All right, the first thing that may not be apparent to you right now. So hopefully we can get kind of this first page done and then we can take a break. The first thing that might not be apparent right now is we don't really have a formula for what this is. You might be able to see it from what I've got written up there. But let's talk about an area formula, because for the theme, I'm trying to make everything very, very similar as we roll throughout the units. You may have been noticing that I'm setting up an area formula and then I'm shoving that inside an integral to get a volume. Well, these shells, I know I made that one like 0.1 thick, but you want to think of these as being like infinitesimally small. So it's very, very thin. So again, that analogy of like the paper wrapper on the can is what you want to think of. We've got this cylinder wrapper. So I'm going to draw this for a second. We need to find a formula for it. So I would like you to imagine you got a cylinder. Oh, I have paper right here. You've got a cylinder. Yes? Wow. I'm great at making props. If I cut it and I let it go, what shape will it be? A rectangle, right? So, rectangle. So my area is really going to be a base times height. The height will just be the volume. What words am I even trying to say? The height is just going to be the height of that cylinder. Now, the question becomes, what is kind of the top part, this length of this rectangle? All right, I would like to argue that it is the circumference of this circle. Now, what is the formula for circumference of a circle? 2 pi r. If you ever forget, take a derivative of the area of a circle. Fancy. So if you're looking at this guy, you're looking at 2 pi r(h). Now, fun fact, just in case you weren't aware, I have now taught you everything from AB. So this is new stuff from the year out. We didn't learn this last year, and everything I teach you from here on out, you will not have learned before. No, integration techniques is all BC. So the thing we just tested on is all BC. I like to move stuff around because usually some people teach differential equations, then this, and then integration techniques. But whatever. So this has been new for you for a while. Wow, way to go. Well, now we're all in this together now. All right, so 2 pi r(h) is what we're going to be working with. I'm going to draw a couple of pictures. I'm going to tell you kind of how I label them. Really, in essence, we're going to focus a lot. I know we're going to do X's and Y's, but really when I use shell method, this is really to get around having to do stuff in terms of Y as far as washer method goes. So we're really going to focus on the X ones here, because usually I'll use this method so I don't have to work in terms of Y for disk and washer. So that's kind of the nice part about this. So again, I'm just going to draw a random region here. You can draw anything you want as long as it has like a defined region and 2 intersection points. And then I'm going to draw a line that I'm going to rotate this around. I'm going to draw that right here. Again, just like last time, it can be an axis, like the X or Y axis, but it doesn't have to be. So this might be the line like X equals 1. Yeah. Yeah, and we'll do both today just so you can see. I might try to scrounge up. A few years ago, I taught this. It was in like 2019. I taught this after the AP test to my AB and AD students as like a preview to BC. And one of our quizzes, I had literally everything could be done with shell method or washer method, so you could practice both, which is really cool. Because a lot of the time you can do both, just one's a lot easier than the other. All right, so one thing we're going to be concerned with, I'm going to kind of draw a representative shell here. One thing we're going to be concerned with is the height between the two of our functions. So this is going to be the height of our guy. And before you start drawing, let me kind of show you a couple of things. This shell is going to go, so I'm drawing kind of the top of that cylinder, trying to center it on the axis of rotation. There's going to be a similar height over here, and you've got something like that. Now, when we're thinking about these shells, it's kind of like we're nesting them in each other. So you've got, like, think of if you had the can in the middle that represents your hole, and then you've got labels that are going out and out and out, and they're changing kind of like their height as you go along. Either way, the line that's going to represent our radius is a little bit interesting. It's going to go out from our axis of rotation out to this height right here. So the two lines you're going to often see me draw are kind of in this like T shape. One that's going to go just somewhere in my region, the same kind of vertical line that I've been drawing this whole time. And then I'm going to usually draw for my radius this line that kind of goes back to my axis of rotation. Yes, ma'am.
So the function that is on the graph is just so you can find the height. Like it's always going to be that shell that is always going to be like that. It's always in that.
Yep. And if you're thinking about it, we're kind of going to be drawing successive cans on top of that.
Yeah.
So it's kind of layering on top of itself. Yep. So your integral is going to kind of layer those up. So we're just finding one representative label, if you will. It'll make more sense once we do at least one question. Right now, we're kind of just labeling. For here, I can do this also in terms of y. Again, I'm just drawing a representative region. Here, if we were going in terms of y, we'd actually be going around a horizontal axis. Again, this could be the axis of rotation, or it could be the x or y axis as your axis of rotation, or it could be something different. It could be anything horizontal or vertical. Again, a guarantee that we're not going to be doing anything slanted. So for here, the height would be going kind of left and right like this. And our radius would be going from this line down to the axis of rotation. So kind of a height and a radius. If you were trying to draw kind of that representative shell, if you will, this guy would kind of go down around, again, trying to center that around the axis of rotation if you're trying to visualize. Now, once I've kind of got a visual of what's happening in my head, I honestly don't draw these shells all that often. I kind of draw that T shape in there, but I'll be drawing some of those today just so we can get a visual of what that shell is, because it does look a little bit different than the discs and washers that we've been drawing before. Another thing to note, we talked a little bit last class about how the order of our subtraction, especially inside those squared things, wasn't as important because we could square it out and it would be positive. Notice that R and H are both singular terms. They're not squared at all. So the order of our subtraction is really going to matter here, because if we subtract the wrong way, we're going to get a negative answer, which is no good for volume. So I've got some shortcuts here, but I kind of want to just talk out the first couple examples. I will say the thing that's going to be the most confusing is probably the radius. So we're going to talk about that the most. The height honestly looks like a lot of what we've been doing before. It looks like a top minus bottom with our functions, and it is going to be that. Yeah.
So is the height parallel to the radius?
Like perpendicular? Yeah. Yes.
Well, yes. I'm sorry.
Is the height parallel to the axis of rotation? Yes.
So is the axis of rotation here? So that's basically how you.
Yeah. So you're noticing the key difference between shell and washer. Here we're rotating parallel to the axis. In disc and washer, we're rotating perpendicular. And that's what allows us to use the letter kind of that's opposite of what we're rotating. All right. Let's actually do a question and figure out all of this before we freak out. Looking at you. All right, so let's talk about this question. This is a really good example of one that would be difficult to do with our washer method. It wouldn't be super difficult, but at the same time, wouldn't love doing. Oh, actually, this one's impossible. What am I saying? So if I want to go around the y-axis, that's this line right here. We're going to go around that one first. Notice if I tried to do our washer method, our two radiuses would look like this. Specifically, I would have to be working in terms of y here. I'd be rotating like this. You don't have to draw this because I'm going to erase it in a second. I'd be rotating like that. I have a problem. Look at this function. Does anyone know how to get that in terms of x equals something with y's in it? No, I don't either. There's not a way to do that. So in this question, if I want to rotate around something vertical, I need to use x's. So this is a good example of a function where I would have to use shell method to be able to do this question. So we're going to rotate this around a couple of different lines so that you can see what's going on. So my shell, I'm going to draw just that line in there. That's going to be my height. Again, drawing anywhere in the region, not really caring about that. And my radius is going to kind of be back to here. So the shell I'm working with is this guy. If you want to draw the shell, great. Or if you want to just draw your height and your radius, that's cool too. So height, radius. Nope. Nope. So if you want it at the top where your circle is, it's fine. Or if you want to draw it somewhere else, that's fine too. All right. Area formula, 2 pi r each. If we're deciding to use shell method, that's the one we use. We have two things that we have to find here. Both can be evaluated with a top minus bottom. I'm going to explain the radius in two ways, though, because sometimes the top minus bottom helps. Sometimes a little bit of a different explanation helps. So let's start with the height, because I think that one's easier. The height is from this guy down to this guy. We've done this a million different times with a lot of our top minus bottoms. What do you guys think the height will be in the context of this question? So I'm looking at the height here, top minus bottom. What's the top function? X cubed and then minus 0, right? We're going down to the x-axis. So that should feel very much like before. We've got top function minus bottom function. Now, the weird part is the radius, because the radius of this cylinder is going to change as we go throughout the integral. It's going to start being 0, and then we're going to have one that goes out, one that goes out, one that goes out, and they're going to layer up as the x's change. What I would like you to consider is that this distance right here, if I had my pen and not my eraser, is the x distance that I am traveled out. Wherever I am, as I'm integrating, that distance is x. So this is going to be our variable of integration. If you want a top minus bottom situation, you're liking that theme, you're always going to use your variable of integration minus your axis of rotation. So sometimes I like to consider this distance x, my axis of rotation, I'm doing x minus 0. If you want to think about distance, that distance is x, and then we can adjust if our axis of rotation is different. All right, as we transition to volume, I like to factor my 2 pi out and simplify as I plug in. So I'm going to drop those minus zeros as I go in here. And my last decision is just these bounds. As we've discovered with a lot of our stuff, the bounds are very region specific. So the region in the XY plane, not our shell, is going to determine those bounds. Anyone got some thoughts? 0 to 1. We're still working with our x values, so we're going from 0 to 1. Yes. No. And we're going to look at the differences in R right now. That's a great question. Good segue. Yes. Yeah, so let's investigate. Really, the big thing that changes for shell method is this radius as I change the axis of rotation. So let's talk about that change as we kind of move forward. So I'm going to change the axis of rotation twice. We're going to do one that's to the left of our region right now, and then one that's to the right, so you can see that change. Yeah. So it's like the rectangle if you unfold it. Exactly. All right. All right. So we're going to now change our axis of rotation. I'm going to move it over here. One thing I want you to notice, height, still going to be the same. If we're using the same little place, radius, do you agree the radius is going to get bigger? Yeah, I am not really drawing it to scale. That thing should be centered around my axis. I just got a little scared. Go ahead, redraw it. Still not even far enough, but closer. All right, so if I'm using the same representative place, I do notice that this radius is getting quite a bit bigger. Height is still going to be staying the same. So my radius is going to go all the way over here. All right, I'm still using 2 pi RH because if I cut this shell, it would still be that rectangle. All right, do you guys agree with me that the height of this guy should stay the same? It's still going to be x minus x cubed, then all the way down to 0. So even if I move the height line, the top function is still that graph, bottom function is still that x-axis. So even if I change the drawing, top minus bottom will still preserve that. I'll just be at like a different x value within my bounds. Now, the radius, there's 2 ways to think about this. If you're thinking purely top minus bottom, you're thinking variable of integration. This x is wherever I am in my bounds, minus the axis of rotation. So I'm doing x minus -1. Sorry for touching that. Kind of helped. All right. So I could do x minus -1. Another way to think about that is this distance right here is my x. How far is this distance? 1. So I have x plus the extra 1 going back from 0 to my axis of rotation. So whichever way you want to think about that is perfectly fine. Wherever you are from the y-axis over to where your representative shell is, that's the x distance. It's going to represent whatever bound you have. Here, we have to add that extra distance 1, but we can remedy that by doing x minus -1. That was our axis of rotation. Yeah, so because this is farther away, you have the positive one as the distance. I love the theme of top minus bottom, so I'm always doing x minus my axis of rotation, but it turns out to be the same thing either way. All right, thoughts on bounds? Are we going to change them? All right, let's think about the x values that we're using for this line right here. Can that line still only go back to 0 and out to 1 to fit in our region? Yes. So just because we changed the axis of rotation, those bounds for everything we've done have been region specific. They are only where that region is, so they will stay the same no matter what. All right, let's do one more crazy thing. Do we hate it yet? Do we like it yet? Hated it before we started. Excellent. Yeah. So our x is whatever distance we are until we hit that height that we've drawn in. It'll change based on the x. Think of the bounds of your integral are like the x values that we're going through. So as you take successive ones, it's going to change that x value as you go through.
Like I understand the one, like the bigger one, the radius is the one and the x.
Mm-hmm.
And so, like, why wouldn't all that can't be x is not in the function. So only if it's in the function, it's x.
Yeah, so your x distance is from the y-axis to wherever you draw it in the region, because the bounds are going to pull you between 0 and 1.
Okay. I understand.
So, like, for example, yeah. Yeah.
That's that radius. So I'm like,
Yeah.
why? But I understand. So it's basically from the height to the edge of the function, and then the rest of it would be whatever distance is left on the axis. Because that's not changing, only the radius. Okay.
Austin, sup? Why? Oh, notation mistake, yellow highlighting. Oh, silly girl. All right, another way to check your radius, I was kind of thinking about this while I had some questions at the front. Thank you, Austin. Is to plug in an x value and check that your radius is correct. So our x values are going to go everywhere between 0 and 1 for our bounds. Let's say we took a radius and we were checking at like x equals 1/2. If we had x equals 1/2, we're looking at that specific shell, our radius should be that 1/2 plus 1 more. So it should be 3/2. If you plug 1/2 in here, you can see that the radius is the right number that you want. So if you want to, choose a specific value of x, plug it in, and see if the radius is what you would expect it to be for that shell. All right, what I'd like to do, just like last time, is I'd like to move my my axis of rotation to the other side of my region and see what that does. Again, the radius is going to be the big changing piece here. There's a couple ways to think about it, so I'll explain it a couple of ways. We're still going to do shell method because we're still trying to rotate parallel to our axis of rotation. So we've got 2 pi r/h. Here, we're trying to rotate kind of like this. So would you agree with me if I'm working with this same representative shell, are we still like in the height equation? Yeah, so the height in this one, very region specific. So we still got our 2 pi, our r is our big question mark, and x minus x cubed down to 0. That's still all good to go. The radius now is a question mark. So a couple of ways to think about it. The easy pattern way, you're going top minus bottom with your axis and your variable of integration. Now I said it in that direction this time because you agree that our axis is actually top and our variable of integration is bottom. Yes, so I could do 2 minus x. Some distance sense making though, this distance right here from 0 over to 2, x equals 0 to x equals 2, that whole thing is 2. And then wherever my x distance is, I want to subtract that out. So again, the example of, let's say we're at x equals 1/2, we would want to take 2 and subtract that half to get the kind of 1.5 distance that we would expect. Yeah. Okay. Cool. 2 minus x. Cool. Are the bounds going to change? Should I write a dx? All right. So let's just make a quick comment. Things that I would expect you to be able to integrate by hand. Definitely, maybe. Here you have to FOIL these out. That is a little obnoxious. Not the worst thing in the world, but probably not super fun. This one you're just distributing. So if I'm going to ask you to integrate one by hand, probably more like that.
They ask us.
Maybe. Depends. Mm-hmm. So your x value is rolling anyway between 0 and 1. So what you can do just to check that your radius makes sense is just to pick any x value within that region and see if the radius that you would get kind of makes sense. So if I'm picking like x equals 1/2, I would expect the radius there to be 1.5 because I would need to go the half and then the 2. So plugging in 1/2 to 2 minus 1/2 would give me that value that I'm thinking of. So you can kind of pick a concrete value to check with.
Because 1/2 is the radius, the other, that rest of that side is a half, and the other side is 1.
Yep, so that's a really good way to kind of check this thing to see if it's doing what you think it's doing.
Okay, that makes sense.
All right, last thing I want to do, and I'm actually going to redraw my little region down here. So excuse my terrible sketch, but this is that region again. What's weird about the last line I'm asking? Yeah, so this guy here, I have us going around a horizontal line. That's new. We haven't done that yet. Oh, wait, we kind of have because we're not going to use shell method. If I wanted to use shell method for this one, going around the x-axis, don't draw this, I'd have to go horizontally and I'd have to use y. We established, though, that we weren't using y in this question because we can't get this in terms of x equals stuff with y's in it. So here, just a reminder, just because I've taught you shell method doesn't mean that washer or disk is not a good method. So let's see if you guys remember anything from last class. All right, I like to go around this line. Questions? Hole or no hole?
No.
Yes.
Can't be wrong, but
No hole. Why? We're touching the axis of rotation the entire time. So I'm going to draw a representative radius in here. If you would like to, you can draw a representative disk. Not washer because it has no hole. And now we're working with pi r squared. Thoughts about the r? All right, whatever minus whatever, good start. Top minus bottom. Minus 0, we're going down to the axis. Here, we want just regular pi. We got x minus x cubed, quantity squared, falling definitely into the maybe category of integrating because I'd have to FOIL that out, so that'd be aggressive. Probably not on my test this time. Fair game probably for a harder multiple choice or for your response on this topic on the AP test. Thoughts on bounds? 0 to 1, very region specific. So as long as I'm using x with this region, they're always going to be 0 to 1. Yeah, so the directions, if we were taking it here, there are a couple options. Technically, I'm not following directions because if it says find the volume, I should be providing a number. So the directions I'm really following here are set up but do not evaluate, which will be a lot of these directions. A lot of the time, especially for the rotations, you're going to see set up but do not evaluate because the integrals get nasty quick. If you see find on the calculator section, I would plug this directly in, 3 decimal places, I'm done. Or every now and then find, you're going to have to do integral by hand. Ashley. Explain. So yes, so here, because we're switching methods, we get to preserve our variable of integration. So because we're preserving the x in our integral, we still get to use the x 0 to 1 here. If I had switched to anything in terms of y, so like all of these, if I had used disk or washer, if I was allowed to and switched to y, I would have to change my bounds there. Good question. All right, can we start these ones in terms of y? Let's see how we're doing. Yeah, let's do it. You guys begged for extra minutes on your round 2, so I get them back. No breaks.
I don't think those actually.
All right, here is a good example. Here's a good example of obnoxious to do in terms of x and disk and washer. Possible, but obnoxious. Let me explain. Here I'm going to be rotating around a bunch of horizontal lines. that means I could rotate like this. That looks fine until I realize I've got kind of two different sections going on here. One section that would be guided by our y equals x squared or x equals square root of y, and one section that would be guided by that y equals 4. Personally, for me, I like to avoid setting up two different integrals because that just feels like an invitation for mistakes. So I would like to try to use this kind of thing, because no matter where I put this line going up or down, there's a consistent function to the right and a consistent function to the left. Here, this is more of a choice, though. I could get these functions in terms of y equals something with x's in it. Just as easy, it would just involve multiple integrals. So let's go around the x-axis first. These are going to go a little bit faster. If I get done with these 4, I promise I'll shut up. All right. So there's kind of my radius. This is going to functioning as my height. Another reason I kind of know that I'm looking to do shell method here in terms of y, look how they gave me that function. They're kind of hinting me, hey, you might want to think about going in terms of y. That might be like a cool idea. All right, thoughts on radius or height? Anyone want to claim either one? R is y. I love it. Just like before, our radius is going to be either shortcut, our variable of integration, we're going to be working with y, minus our axis of rotation. Here, the x-axis is that y equals 0. Or this is our height in y here. Whatever y value we're currently at, that's going to be the radius of our shell. Perfect. All right, thoughts on height? All right, you should be saying stuff with y's in it, hopefully. What's the top function, meaning the function farthest to the right? 7. There we go. All right, so we're talking 7 minus square root of y. We got to have square root of y because depending on what y value we're at, that's going to change the height of that cylinder. As we transition to volume, hopefully you guys were listening to the question Ashley was asking before we turn the page. What are our bounds? Good. 0 to 4, not 0 to 7. We're working in terms of y, so we need to go up and down. Again, you can still use that pencil trick. Lie your pencil along the height, the thing in your region, slide it up and down. You should be going between 0 and 4. All right, let's adjust. I want to change our line to y equals -3. So that's going to be down here. So height, radius. Okay, radius looks like it's getting bigger. Yes, good notice. No. 2 pi RH. Did anyone notice what stayed the same last time, no matter what? The height and the bounds. Good. We were doing a lot of staying the same. Height here, still going to be top minus bottom in my function because that height is within that region. So 7 minus square root of y still works. Radius was different. Cool. So a couple of different ways to think about it. We got y, that was this distance, plus 3 to get down to that axis of rotation, or if you're doing a top minus bottom, our variable of integration y minus -3. Same bounds? Just so Austin can be sassy again. Did I forget anything? Thanks, Lily. I meant to tell you, I wasn't feeling well last week, so I dressed up in all black. And it made me feel a little bit better. A little angsty. That's fair. All right, let's move our axis up. All right, so let's go with the same representative height, just to illustrate a point. Radius. Our picture's getting complicated. The nice part is if you actually do this on your own, you're not going to be asked to rotate around a bunch of different lines. It's just good practice, good way to see patterns. Anything going to stay the same? Height. H, still this line. Yeah, I tried to write over it. Didn't really work. All right, thoughts on radius? All right, which one is it? Is it y minus 4 or 4 minus y? 4 minus y. And this time it matters. No, I'm glad someone said that because it's important. It's really important for this method because it's not squared. So if I do it wrong, I have to make sure. Again, a great way to check. All of our y values are between 0 and 4. Let's pick one in the middle. Let's pick 2. If we had done y minus 4, that would mean 2 minus 4. My radius is negative 2. That doesn't feel right to me. So feel free to plug in something to check your work. I'm going to plug this in. B equals 2 pi, integral 4 minus y, 7 minus square root of y dy. Bounds the same? 0 to 4. Are they talking about calculus? Not at all. I thought they were. I was really excited. And then I looked up and it wasn't at all. The disappointment and disrespect. All right. What time is it? Oh, I got just enough time. No.
Oh, yeah. 1 minute.
Yeah. Go. All right, let's pretend I'm going around the y-axis now. Again, I would prefer not to have to work in terms of x in this question because I have 2 separate blocks of what's happening. One function is controlling from 0 to 2. One function is controlling from 2 to 7 if I'm working in terms of x. Here, though, if I worked in terms of y, I can have one consistent top function and bottom function as far as this goes, but I would be forced into working with washers instead of with shells. So here I would want to do my pi r squared. Would you agree with me that there's going to be a hole in the middle of that though? Cool. All right, so I would want a pi big R squared minus a pi little r squared. Big R squared, I'm going to go from 7 back to the axis, which is 0. Little r, I'm going to go from that curvy function back to the axis. That curvy function was our square root of y. Transferring to volume, I've got 2 pi. No, I don't. I lied. I've got 2 pi's that I'm factoring out, so just one singular pi. 7 squared is 49. Square root of y squared is y. So this one, a good example of something I would ask you to integrate by hand. Thoughts on bounds? 0 to 4. Again, region and variable specific. Since that region's the same and I'm still using y, it's still 0 to 4. All right, I think I'm going to save this question at the bottom for next time to illustrate kind of just again what we could do. Yeah, I can definitely. Before we leave though, pretty please. Bring your problem sets next time. Arc length is the last. Wow, we're already at the end of unit 7. I know. I'm not really sure. Unit 8's really long, so we may push into Unit 8 a little bit before we take our Unit 7 test, just to... honestly, did someone say partner test? Honestly, I'm pondering it. No. So I'll have dates for you next class. Just know that we won't test at least until a couple of sections into Unit 8. Also, that test is going to be highly calculator active, but can everyone just look at my face and stop moving for approximately 1 minute? We still got about 3 minutes left of class. please bring your problem set next class. Arc length is a very short section. I can probably teach it to you in about 20 minutes. That's being optimistic. I like to talk too much, but I'm going to try to make that lesson as short as possible to give you as much time possible to do your problem set next time. I really like the problem set questions that I chose, meaning I don't really feel like creating new ones for notes checks. So we probably won't do a notes check next time. We're probably just going to do quick notes, problem set the rest of the time. That's kind of my plan. I'm hoping to get your test graded by next class, maybe? Question mark. Hoping, but they'll be graded within. Yeah, Connor. I just realized that no, but I will try to have them up by the end of the block online. If I don't, feel free to email me to remind me. Cool. Last things, thank you for your hard work on the Unit 6 test, whether you are proud of it or not. Great job attempting that. I like it. If you are still missing that test, be talking to me so we can get that done. Have a lovely weekend. We got about a minute and a half. I'll see you next time. Hello. Yes. Okay.
I know. That's like